Hello, College Algebra. Hope you guys are doing all right. And today we'll be starting the video for 5.2 applications of exponential functions. I do want to let you know this lesson is going to be a little bit long, so I'm going to be actually splitting this lesson up into 3 videos, and this is going to be the first video. And each video is going to have its own special topic. Today, the special topic is going to be radioactive decay and a little bit of concentration as well. We'll talk about that later. But mostly today's topic will be radioactive decay. Another video, we'll talk about population growth. And then on another video, we'll talk about compound interest. And throughout these 3 videos, we'll be throwing in a couple other quick lessons as well. But besides that, that's what's going to be. That's what's going to be happening. We'll have 3 short videos just to break down this long lesson, and it might be easier for you guys that way. So with that said, let's go ahead and begin. Today, again, as I said, this video is over radioactive decay. So what is radioactive decay? Radioactive decay, it is the technique used by archaeologists and anthropologists to estimate how long ago an organism died. So like say you have an anthropologist and they find a dinosaur, but they find the skeleton of a dinosaur, and what if they want to figure out, well, how long ago did this dinosaur die? Was it a billion years ago? Was it a trillion years ago? Who knows? But it turns out we can actually do some mathematics and a little bit of chemistry to help us out. Living organisms constantly absorb the radioactive substance carbon-14 while alive. But the intake ceases once the organism dies. Determining the amount of carbon-14 left in the remains of an organism can actually help estimate when the organism died. So let's say when the dinosaur was alive, it had 10 grams of carbon-14. And then a million years later, or a billion trillion years later, it only has maybe 1 gram of carbon-14 left. You can use a little bit of mathematics to determine, oh, this dinosaur died a trillion some years ago, just to give you an example. But let's go into the specifics of how we compute that. So the math behind this, the math of the age estimation depends on the fact that half of a given mass of carbon-14 decays over a period of 5,728 years. In other words, after a period of 5,728 years, the amount of carbon-14 in a dead organism decreases by half. This is known as half-life. And every substance has a different half-life. So just to give you an example, let's say that you have a dinosaur, let's call him Dino, and let's say he died some trillion years ago, and at the moment he died, he had 10 grams of carbon-14 in the system. But now let's skip forward a little bit, and let's say we go to 5,728 years later and see how Dino is doing in terms of his carbon-14. I got 5,728 years from up here. So let's say 5,728 years later, he now has 5 grams of carbon-14. Basically, after that many years, the amount of grams he had was cut in half. Whoops. But it doesn't stop there. Let's say we wait another 5,700 years later than that. Then let's see how Dino is doing. So another 5,728 years would decrease his carbon-14 down to 2.5 grams. Basically, it's taking the half of 5. And of course, the pattern would continue as well. Let's say we wait another 5,728 years. His carbon would decrease by half again, down to 1.25 grams. I think you guys are recognizing the pattern. It's basically being cut by half every time period. So that explains the half-life. And specifically for carbon-14, the half-life is 5728. So now that you understand the half-life and what it represents, now let's use it to help us calculate more specifically the amount of grams that will be left after so many years. So this is the equation. If you go up here, this is the equation that anthropologists use involving half-life. And that's probably a lot of letters that you may not recognize at first. But I'll first break down each of those letters. First, we have the power of t up here. Of course, that would represent the time. I'll get to the little a later. Right now, I want to look at a sub 0. A sub 0 is a symbol or letter to represent the amount of carbon-14 at time equals 0. Or in other words, it's describing the amount of carbon-14 right when the dinosaurs die. Or basically, the moment the dinosaur dies, you would say, okay, the dinosaur is dead now. It has 10, 20, 30 grams of carbon-14. And then the next symbol, a parentheses t, that represents the amount of carbon-14 after so many days or years have passed away. So in other words, say you're a trillion years into the future, you're now looking at the dinosaurs and saying, okay, it started with maybe like 30 grams of carbon. How much carbon does it have now? Because I'm sure a lot of that carbon has decayed after so many years. So that's what each of those symbols represents. But now you're probably wondering, what does this little a represent? Little a in this formula is actually the number that helps determine how fast or how slow the carbon will decay. And it involves using our half-life. And just so you know, there is a special formula to find little a. It's right over here. To find little a, what you got to do is you got to take 0.5, and then you're going to take that to the power of 1 divided by h, where h is the half-life that we talked about in the previous slide. So I'm going to first get you familiar with how to compute this little a. And I'll show you how to do that on the next slide. So let's say on the Hawks program, you're given this example, that the half-life of carbon-14 is 5728 years. And it's asking you, determine the base A so that for this function that we talked about, it will accurately describe the decay of carbon-14 as a function of t years. So again, the formula for this little base a that it's asking for in the instructions is you take 1/2 or 0.5 and you raise it to the power of 1 divided by your half-life, which we'll call big H. And my recommendation when you plug this into the calculator, you take the 1/2 and rewrite it as a decimal. And in the calculator, I strongly recommend you do this. Put the 0.5 in parentheses, then you'll raise to the power, put in parentheses 1 divided by whatever your half-life is. I strongly recommend you use parentheses because if you don't use parentheses, your calculator will compute it wrong because your calculator does not assume the order of operations. It's actually kind of irritating. But anyway, for this case, what we're going to do, parentheses 0.5 to the power, didn't mean to do that, to the power of 1 divided by our half-life. And our half-life, let's look at the instructions. The half-life is 5728 years. And you can go ahead and keep that in terms of years. So go ahead and do 5728. That is what will be plugged into the calculator. And again, parentheses. So let's do that in the calculator. And again, if you don't have a calculator at home, you can use this calculator. It will perform everything you need to do. just go to eeweb.com/tool/calculator, and it will take you to this calculator. And it's actually very useful. So let's go ahead and do what we need to. Parentheses, 0.5, close the parentheses, then to the power using this button right here. Oops, too far. Let's do that again. 0.5 to the power, parentheses, again, please do it, 1 divided by 5728. There you go. Once you have all that written out nice and neatly, you can go ahead and press enter. And that will be our little a. Yeah, it looks pretty yucky, but that usually is a good thing if it looks that yucky. And in terms of the Hawks program, they will want you to round it to 6 decimal places. So 1, 2, 3, 4, 5, 6. This is the 7th decimal, which is a 9, which we'll want you to round up. So when we put this in the Hawks program, we'll say 0.99879 when you round. And there you go. That's what we'll put in the Hawks program. That little a is 0.999879. And that's how you find little a. You just use that formula, type that in the Hawks program, and that's an easy point. Easy as that. Let's do another example, only this time, let's find the little a, not for carbon 14. Let's look at a different element. What about radium-225? The half-life of radium-225 is approximately 14.9 days, not years, days. So in other words, it only takes approximately 2 weeks for radium to decrease by half. So the first step for this equation is we are going to determine little a for this formula. So we're going to find little a to describe the amount of radium-225 left after 2 T days. And again, I already got the formula for little a written for you, because that's what it's asking for. It wants little a. And in this case, when we find little a, we'll do 0.5 to the power of 1 divided by the half-life, which in this case, the half-life is 14.9 days. And don't worry about changing that to years or days. Just keep it as it is. So keep it as 14.9. All right. So that's what we'll type to the calculator. Let's do it. Erase the previous answer. Okay. Clear. So again, parentheses, 0.5, close parentheses, to the power, close parentheses, 1 divided by 14.9, close parentheses. Double check that all looks good. 0.5 parentheses, power parentheses, 1 divided by 14.9. Press enter. Press enter. And that's going to be our little a. Again, it's supposed to look yucky. And again, we'll round to 6 decimal places. 1, 2, 3, 4, 5, 6. This is the 7th decimal right here. 5 and above means I got to round up. So 0.954546. That is my little a. 0.954546. All right. We'll go ahead and write that down right here. 0.954546. That is little a. That is what will go into the Hawks program to get yourself an easy peasy point. Okay, so that's step 1, finding the little a. Now, there's this part 2 to this problem. So we're still talking about the half-life of radium-225, which is approximately 14.9 days. But now step 2 is asking something different. How much of a 6-gram sample of radium-225 would remain after 8 days? Round to 3 decimal places. This is where that actual formula is going to come in, where we talked about what a sub 0 was, what a sub t was, and what time was. So to start off, you already found what little a was. You found that on the previous slide. That was 0.954546. That was already done. You already found little a. And of course, you know that t represents time. So in other words, whatever little a is, we're going to take that to the power of whatever the time is. If you look at our instructions, it tells us that we're concerned about what happens after 8 days. So 8 would be your time. So in other words, little a to the power of 8, or 8 days. And then the a sub 0 is going to be multiplied in the front. And remember, a sub 0 is the starting amount of the element that we have. And if you read the instructions, it says how much of a 6-gram sample. So in other words, we're going to be starting with 6 grams. After 8 days, the 6 grams of radium is going to decay, and there's only going to be a certain amount left over. And we will find how much, or we'll find the amount left over once we do all this calculation, just like that. Now, I have to ask you guys something. What do you think I should do first? Should I do 6 times the green first? Or should I take the power first? Which one do you think do I have to do first? Or does it even matter? Give you time, a moment to think about that. If you thought about it and you want to check your answer, here's what I recommend. Remember PERMDIS. P is for parentheses, exponents, roots, multiplication, division, addition, subtraction. And in this case, take a look. Exponents become before multiplications. So in other words, exponents should go first. And once you've done that, then you multiply. So let's go ahead and do that. Let's do the power part first. We'll take little a to the power of 8. So let's go back to our previous slide, or let's go to the calculator and compute that. Okay, I'm going to erase this. So let's do our little a to the 8. And you can do the rounded version, that's fine. So 0.954546. 954546, yep. And then raise that to the power of 8. And then press enter. And you're going to get that really huge decimal. Yeah. Oh, Miss Sheila, do I have to write all that? Technically, no. So let's just say you got that gigantic blob from the calculator. But remember, once you have that blob, all that's left to do now is just to multiply that blob by 6. So let's do that in the calculator. Let's take that gigantic blob, and so let's take that gigantic blob, or the previous answer, and then multiply it by the 6, or the 6 grams. Press enter, and you have your answer. That's how many grams are left over. And let's look at the instructions real quick. How much are we supposed to round? Look at the instructions. Round to 3 decimal places. So going back to the calculator, the number of grams left over after 8 days is going to be 4.135 if you rounded 3 decimal places. Because this is the 4th decimal. 4 below means you keep it as is. So 4.135 grams is left over. Oh, sorry. So that would be our answer. Type that into the Hawks program. 4.135 grams, and you're good to go. All right. Let's try one more example similar to this, and then I just have a quick offside example, and then this video will be good to go. Okay, next slide. One more time. This time, our element is going to be aluminum 26. And the half-life of aluminum 26 is approximately 730,000 years. Woo, that takes a long time for this to decay. Woo, that means it's pretty tough stuff. So step 1 says we're going to determine the little a for this formula. And of course, remember the formula for little a. You do 0.5 parentheses to the power of 1 divided by your half-life. Which in this case, our half-life is a biggie. So 0.5 to the power of 1 divided by the half-life, which is 730,000 years. This is going to be fun. All right, let's see what that does in the calculator. All right, we're going to clear all that, erase all the red notes. All right, let's see what that does in the calculator. So 0.5, close parentheses, to the power of 1 divided by 730,000. All right, close parentheses, 0.5 to the power of 1 divided by 730,000. Perfect. Woohoo! And that is our little a. And we're supposed to round to 6 decimal places. 1, 2, 3, 4, 5, 6. That's the 7th decimal. 0 is not going to tell me to round up. So I just get a bunch of 9s. Interesting. And no, you cannot round it up to 1. You got to keep it as 0.999999. Okay, so there you go. That's little a, 0.999999. All right, put that in the Hawks program, easy point. That's step 1. Now step 2. We're still with aluminum, aluminum 26 with a half-life of 730,000 years. So now, how much of a 14-gram sample of aluminum 26 would remain after 5,398 years? Okay, we got the information. Let's plug in everything. Little a, we just got that from the previous step, 0.999999. The time that we're given specifically is 5398. So little a to the power of 5398. And then the amount that we start with is 14 grams. So after that many years, how many grams will we have left over after some decaying? And again, you do exactly what we did on the last example with radium. First, according to PERMDIS, you gotta do powers first. So little a to the power of that. Okay, let's see what that does in the calculator. All right, so 0.999999 to the power of 5,398. All right, let's press enter, and you get that gigantic blob. So in other words, we just got that gigantic blob in the calculator, and now you just got to take that blob and multiply it by 14. Let's do it. So in other words, take that blob, or the previous answer, and we're going to multiply that by 14. Press enter, and that's the amount of grams that we'll have left over. And if you read the instructions for our final answer, we're going to round it to 3 decimal places. So the amount left over, round to 3 decimal places. 6 is the 4th decimal, which means I have to round up. And that's going to give me 13.925 grams. That's how much is left after 5,000-ish years. So then in the Hawks program, you will put 13.925 grams, and you're good to go. It's literally as easy as that. The only thing that might trip you up is that if you're going too fast with the calculator and you type the wrong number in or the wrong operation. My advice for these examples, take your time with the calculator and double check that you've typed everything in correctly. Especially with the upcoming example that I'm about to show you. So if you do have the calculator with you, I want you to real quick find this button, the natural log button. And in this case, if you look at the little blue encryption right above it, you'll see a function called e to the power of x. This is actually a function, an exponential function that is commonly used in statistics. It's also used in a lot of science and chemistry classes to help calculate certain problems. So this is where e of x would be if you have one of these calculators. But if you don't have one of these calculators, if you go to the online calculator, your e of x function will be right here. It has a special button just for e of x. So like say, for example, you wanted to find e to the power of 2. You would first type in e. You'll notice it already has the power there for you. You just got to put 2 in parentheses and done. That's how you compute it. So just wanted to show you how to use this because we will have to use it in the next slide. So the concentration of a certain drug, or how strong a certain drug is in the bloodstream after t minutes, is given by this formula, 0.07 times parentheses 1 minus e to the power of negative 0.2 t. Given this formula, what is the concentration after 12 minutes? Round to 3 decimal places. So basically, we're computing how strong a drug is in the bloodstream after so much time has passed away. And I've already rewritten the formula. It's basically the only thing you're missing is the t, which is time. But they do give us that the time is 12 minutes. So you really just got to put in 12 for time, and really all you got to do from here is plug and chug. Now, I must warn you, do not type in all of this all at once. Repeat, I do not, please do not type this entire function into the calculator. Again, the calculator really sucks at order of operations. So if I were you, I would do one step at a time. I would first go ahead and multiply these two together. Multiply that first. So clear, let's do negative. The negative button is right here. So negative 0.2, and we're going to times that by 12. That's going to give us negative 2.4. So I'm just going to go ahead and write down everything else. 1 minus e, and we just multiplied these, get negative 2.4. Okay. All right. So now the next step. We can't multiply anything just yet, not until we figure out all of this. My recommendation next on what to do is let's do e to the power of negative 2.4. Don't do the minus part yet. Just do e to the negative 2.4. So e to the power of negative 2.4, and you should get this. All right. I'm going to go ahead and call this blob 1 because I don't feel like typing that all in onto, I don't feel like writing that all down on here. So in other words, we got 1 minus this whole blob that we just got, blob 1. And then we're still going to have to multiply that by 0.07. Whoops. All right. So now what I would recommend is now I would do 1 minus that blob that we got on the calculator. So in other words, let's go to here. We got blob 1 still there, and we're going to do 1 minus the previous answer, where the previous answer was blob 1. And let's see what we get. We're going to get that number, We're going to call this blob number 2. So let's write that on here. So we still haven't done anything with the 0.07. We just did 1 minus blob 1, which got us blob 2. And now you can finally find the final answer. Take 0.07 times blob 2. So let's go to the calculator. That's blob 2, or previous answer. So let's do 0.07. We're going to multiply that by the previous answer, where the previous answer was blob 2. And press enter. And that is our final answer. We have now computed everything. So the concentration, and let's look at the instructions. How much can we round to? The instructions say round to 3 decimal places. So go back to the calculator. I'm going to round this up to 0.64, because here are 3 decimal places. This is the 4th decimal. 6 and above tells me I got to round up that 3. So the concentration is 0.064. So then in the Hawks program, just write that down. The concentration is 0.064. All right. So most of these equations, it's basically just figuring out how to work with the formula and how to work with it in your calculator. If you mess up at all, if you mess up with anything with these examples, it would have been because you typed in something wrong in the calculator. So please take your time, double check everything you type in, and you'll be just fine with these examples. So with that said, that wraps up part 1, and I'll get to part 2 and part 3 as soon as I can. I'll see you guys later.